Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in a new exciting subject of civil engineering, that is tree structure. Student, basically, I'm doing a basic example, some kind of example of beam design and analysis, basically. So let us come to the topic, that is our major assignment of tree structure, which was given to solve those examples, some of the beam design examples. Okay, so the topic basically today is the design and analysis of beams. Okay, so the first example directly come to the questions. I will do the theory portion and the rest of the tree structures topics as well in my coming lectures, but this is a demand video, so that's why I am doing this lecture as per the students request. Okay, so the first example is also relevant to the basically you can say the design of this is the analysis question. Okay, because you have to check the beam capacity as well as different kinds of strength. The second question is that basically the second question determine if a W, this is also determine its design flexure capacitors by. Yes, this is analysis as well as you can say a design question, because you have to check W1012 section. Okay, this one is also an you can say an analysis question, because you have to determine the value of CB. Now what is CB? And okay, this is a factor, and I will explain this in my coming lecture, coming part of the video. Okay, this example is also analysis question, because you have to find out the flexure capacity. Clear? Inshallah, I will do this example. And the fifth question is that the fully composite section and determine the available strength. This is also you can say an analysis question. A composite section is given, and here this is question number 6. During construction, the steel beams are laterally braced. Determine if the beam is adequate. So the section is basically designed. The same question. This is the same question. The section is basically designed. You have to check the capacity of this composite section. So I will do this major assignment. First of all, I will start my beam design question, and then I will come towards the rest of the topics as well. I will do all the examples. Okay, so let us start. The first question is that I will repeat the question. Determine the lightest W10 section, okay, suitable for the beam shown in this figure. The loading consists of a uniformly distributed dead load of WD, that is dead load, but this is not a factor load, this is a service load, which includes the weight of the beam. Yes, this is a very important term. You should note this that the self weight of the beam, because whenever we are designing a steel beam, we have to include the self weight of the beam. So I will explain this in design portion of the beam. So here, as I am doing just checking the W10 section. So when I design the beam, steel beam, okay, I will explain this point as well. Okay, so in a uniformly distributed load of live load, you have a live load, okay, that is 3 kg per feet. The beam is continuously braced. Okay, so I will explain this term, that what basically this term means, that continuously braced, intermittent braced, and so okay, I will explain this. And its compression flange and has a yield strength. Okay, these are the properties of the section. You see, the beam is uniformly distributed and the beam is continuously braced. This is a very important term, continuously braced. Okay, so let me show that what is a brace beam. Okay, so a brace beam and unbraced beam. Okay, so let me show you that what is a what is a braced structure and unbraced beam. Sorry. So let's say if I, for example, let me change my pen. Why it is not changing? But let me show you. For example, I have a beam, okay, like this one. Let me draw. Uh, for example, if I a beam, okay, and this is supported, okay. Let's say this is a wall, clear. This is a wall, clear, and here we have a beam, clear, and this is a beam, okay. The beam is loaded from the top as well, okay. So you see here that the beam is basically unbraced. Unbraced means whether you have to provide any other intermediate supports, like for example you see a column here, okay, and a beam in between the two columns, okay. So sometime we brace this beam inside, from inside, in the middle or something, some other places, as we do basically in a water tank, okay. So let me show you. For example, if this is a water tank, okay, if this is, let's say this is the top of the water tank, okay, and you see the beams which is used for the bracing of these columns. So you can see here, for example, these are the column bases. So the column is basically supported from the base as well as to the top, but at the middle you see these bracing beams, okay. So basically it 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 provides an extra support to the columns. Why? Because it reduces the segment, like the, you can see the buckling capacity. It increases basically the axial capacity of the column. So the same case is basically, we can say we replicate this same principles on the beam as well. For example, let come to this point, to the beam, okay. So you see here, if we provide some lateral beam to this main beam, for example in this, here you see here, okay, you see here some lateral beam if we provide to this beam. Now the behavior of this beam now will change. Before these lateral beams, for example, the beam will bend in downward direction, as well as it will buckle in this direction, or it may buckle in that direction basically, okay. It can, you can say it will buckle in the horizontal direction, not in vertical plane, okay, because the beam, you can say, for example, this beam is right over here, okay, it can buckle in downward direction, which is basically known as bending, okay. Now sometime when the beam is loaded, this basically happen in steel beams, okay, because you see the steel beam has two basic portion. One is tension portion and one is compression portion. So once you basically you load the compression portion from the top, okay, so the beam capacity is more in bending, okay. The beam cannot bend in downward direction, but they basically buckle, okay, in plane, like the one you can see in 3D view. They will buckle like in this direction or like in this direction, okay. This is in basically horizontal plane, you can say, or it may buckle like this in this direction, okay. So its flanges can buckle, or either its whip can buckle, I think so. I will explain this in later my coming video as well, that what is lateral buckling basically, torsional buckling and lateral buckling, because these two are very dominant phenomena or failures basically of the steel beam, okay. So I think you got something about the this continuous bracing, this kind of bracing. But here they say that you have to provide continuous bracing, means that the beam is laterally braced, continuously braced. Okay, continuously braced means you not provide just intermittent bracing. Like for example, if you provide here a lateral bracing, here a lateral bracing, so you basically tighten the beam in these points as well. You tighten the beam here and here. You can see here these are the extra supports which is provided in plane to the beam. So what basically they did, they increase its supporting, basically they increase their supporting length. Okay, for example, if you don't provide these intermediate lateral bracing, we use the length L in between these exterior support, that is our LB, that is unsupported length. Okay, now if we provide these intermittent bracing, then we use this length, which this one will be our LB, which is our design length of the beam. Clear? So sometime basically we provide continuous lateral bracing. Okay, they basically you can say continuous means you basically insert the top portion, like the compression portion of the beam in a concrete slab, like the one you can see here, this one. This compression portion of the beam is basically inserted into the concrete, so that concrete then provide a continuous bracing. It do not permit the beam to buckle in a lateral direction. Okay, so that's basically increase the steel beam capacity. So inshallah I will explain this in my coming lecture as well. At this point I think this is enough, that you must know that what is continuous bracing. So once you continuous brace a beam, its length you can use LB as the total length. Okay, now this whole length is now effective, and you can use your design length as the whole length, that is, you can see here, that is 20 feet. Clear? So let us start the example. Okay, we have to find basically a lattice W10 section. Clear? And UDL loading is basically given. Clear? And let me change my color. Okay, now live load is given. Clear? Dead load is given. Clear? And the beam is continuously braced, so that why LB is basically, now this LB is basically now 0 because this is unsupported length. Okay, so FY is 50 KSI. Now what is LB? And basically that is related with bracing. Okay, so as I will explain here, that once the structure is continuously braced, your LB will be equals to 0. It must remember, you always remember that when the structure is continuously braced, your LB is equals to 0. Supported length and unsupported length, I will explain this in my coming lecture. So your FY is 50 KSI. Clear? And this is your beam. Okay, now loading is given 3 kip, 1 kip. Okay, that is your dead load, and 3 kip is your live load. Your length is given 20 feet. You have to just convert the service dead load to factor loading. Clear? And you have to find out the moment. Clear? That is, I think this is the same procedure as we did in our PRC2 course as well. WL square, that is a semi supported beam, and you have to did this by this semi supported design formula. Now here the condition. Okay, now let me go to the steel, that is, let me check where I'm working. So we come toward the LRFD manual, and we see that what are these conditions. Okay, And let me show you, this is a manual of steel construction, okay, LRFD manual, and I have as well AISC, that is American Institute of Steel Construction, okay. So I will use both these manuals, okay. So you must remember that in steel structure we use these manuals, and you must be the, you can say, master of these, of using these manual, okay. You must know about each chapter, where beam chapter, where is column chapter, okay. So I will explain these in my coming videos, as well as in my coming topics, because in topic wise, if I explain these manuals, so I think this will be a more easy approach, okay. Because if I start by just introducing these manuals, you don't understand, okay, these manuals, okay, because this is a very containing a very vast material. So we will explain this in topic wise, okay, that where we have, but this is a LRFD manual, okay. We have different chapters, like you can see here, okay. And the first portion of this section, these are related to dimensions and properties, but basically I'm turning you people towards this condition, okay, to the beam chapter, I think. So that is chapter number 4. So let me, where is the cursor, okay, let me show you that where you have your beam chapter, clear. That is chapter number 4, okay. Chapter number 3, chapter number 4, this one, 4, this is chapter number 4, okay. So where the basically the design approach and some basics of beam design is started, okay. So this is chapter number 4, and this one, clear. Here you see the design, and as well as you see the whole principles and equations and formulas of beam design, clear. This is the topic, design strength of beams, okay. These are the general, you students can read this, okay, but I just give you just the summary of this whole topic, okay. You see this figure, this figure is basically very important figure, clear. This define basically that in steel beam have three distinct, the design strength of a steel beam basically lies in the three different zones. You can see the one that is you can say a straight line, then it inclined, and then it has a little bit of parabolic portion, clear. So if I draw basically if I draw this graph over here, so for example you have this one, the ordinate basically show you the strength of the beam, and this abscissa, you can say, or the x-axis basically represent the unsupported length, that is LB, okay. Now you basically see the linear portion, then the inclined portion, and then there is a little bit of parabolic portion, clear. So we have basically three distinct portion over here, three different clear portion, okay. The design strength of the beam basically lies in these three zones, okay. If the design strength lies over here, okay, you can see here there is your LP, clear, which is this one. You can see here LP dash nut, we don't, this one LR, clear, and then beyond LR. So we have basically LP, and we have basically this one, that is LR, okay. So we have basically we determine our LB in this case as LB is basically equals to 0. So we will find LP, we have a formula for this. We will find LR, we have a formula for this. Remember, if LB is less than LP, the strength of the beam is basically lies will be in this zone. If LB is more than LP but less than LR, strength of the beam will be in this zone, okay, which is this zone is basically, you can say, the plastic zone, okay, and this one is basically, you can say, elastic zone, and after that basically it will go sorry, there is a plastic behavior, and there is a elastic behavior, okay. There is a little bit, basically you can see there is a yielding, you can say, yielding zone, you can say. Now the strength of the beam which is in this zone is basically denoted by MP, clear, and the strength of the beam which lies in this inclined zone is basically denoted by MR, okay. So MR is basically limiting zone, okay, and remember that according to these three zones we have basically three sections of beam as well: a compact section, a non-compact section, and a cylinder section. So we will check what is compact criteria, what is non-compact criteria. I will also do that I will also give you some kind of formulas for section, how we check a section of beam, steel beam, okay, as well. Inshallah, you will see coming. But you must know this graph, okay. So this is a plastic zone, and this one is basically, now if you want to find the strength of the beam in this zone, you will use the interpolation technique. So let me show. This is basically a CB. This is a factor. Inshallah, I will do an example, because we have a question number 3, and this I will explain them this term in my coming lecture, okay. The first basically section is, you can see here, that is when LB is less than or equals to LP, mean that when the section lies in this zone, clear, when the section strength lies in this zone, okay, which is the plastic region, the strength of the section will be determined from this formula. Pi B, which is the factor, reduction factor, MP, which is further equal to Z into Fy divided by 12 to convert it into feet, okay. This LP is basically nothing. This is 300 into Ry divided by Fy into root, clear. So this is the formula which is used for LP, that how we can find. The next zone is when LB is greater than LP but less than LR, mean that when the strength lies in this zone, so your LB is basically greater than LP but less than LR, then you will determine the design strength of the beam by this formula. This is an interpolated formula, okay. Now you must remember it, and you must note the difference between these two zones, that the strength will be when the second condition stand or exist, you can say the strength will be less than MP, okay, in this zone, because this is the plastic zone, okay. So somewhere here, okay, now here your design strength, so in this zone basically the strength will be less than that zone, clear. So here you can say MA, okay. Now this is interpolated because it's a straight incline, okay. Now you see here you will use this formula, but this will be less than pi b MP, means the strength you have to check this equation as well, and in second zone your strength must be less than this one, clear, okay. What is LR, you will determine it from this formula, as well as these values can also be determined from tables, okay. So you have to use this formula, okay. What is x1 and what is x2, which is used here, that explain this, okay. And the strength, the design strength is basically nothing, it is in that zone basically, okay. In this zone the resultant strength or the design strength will be this one: pi b MR, pi b Sx Fy minus Fr, that is 30%, you can say, okay. And the third zone is basically this one, clear, compact and non-compact section, okay. LB is greater than LR, means that you come to this zone. Now Now you are beyond this zone. Okay. Now what will be your design strength? Then you will find your design strength from this formula. Okay, you see here, and the different terms will be explained here. Sorry. Yes. Yes. Okay. So the different terms which is used here. Okay, your lambda. Okay, and okay, that this term is basically lambda, which is explained that whether the section is compact, whether the section is non-compact. Okay, so let me show you. This is your LB is greater than LP dash no. Okay, so this is basically third zone. Okay, when your strength lies in third zone, then how you can determine your strength. Okay, so I will explain this in coming terms, but this is a little bit general introduction. Okay, about this that you a little bit idea about these terms, that from where your LB is less than LB, where this condition basically when this condition is basically exist, then why we use this formula. So this is basically the behind theory which I explain you. Okay, so we have different three zones, and here we have basically the strength of the section lies in the first zone. Clear? So LB is less than LP, so pi b mn equals to pi b mp. Basically this condition exists, so the required strength will be pi b fy zx. Now you have to find your zx because you have to check the section W10 section. Okay, so zx mu divided by pi b fy into 12, just plug the values mu pi b, that is 0.9, fy, that is 50 ksi, multiply by 12, 80 cubic inch. Now you will use from Z table of manual W1068 has a ZX value is this one, but this is in 14 edition. Okay, I will show you this. Okay, now let me show you. This is calculated value. Clear? This is calculated value and this is tabular value. Okay, so if you search the ZX table, you just directly found this ZX. Okay, from table as well. You can use the formula. Okay, or either you can use the manual. Okay, so let me show you that where the ZX and from where this value is